Okay, in 7.1, it's basically a review of how to graph inequalities and where to shade and whether we have a solid or dashed line. So this is a review of Algebra 1 and Algebra 2 concepts for this. We're going to start out looking at this line, y equals 2x, 2/3 x minus 3. And that is an equation because we have that equal sign. But when we have an inequality, we actually split the plane or split up our graph into two what are called half planes. We have the values that are larger than our equation and the values that are smaller than our equation. So we have these two pieces. Okay. Now we're going to talk about how to graph those inequalities. So first, we need to talk about the boundary line. When we have just greater than or less than, that means my values on my line or on the equation that you're graphing are not included. That means that you're going to have a dashed line, like the one here. But when we have greater than or equal to or less than or equal to, we have a solid line. That means that the values that are on the line, the values that make that equation true, are included in my solution. Now, the solutions to an inequality are not just the points on that line, on that boundary line. What we actually have are regions of solutions. So how do we know where my solution region is? Well, that's where we have a couple different methods. Our first method is testing a point. So we have our inequality here, y is less than or equal to 2/3 x minus 3, and they've chosen to test the point 0, 0. That means that they are plugging in 0 for x and 0 for y, and then figuring out whether or not that gives us a true or false statement. So you can see here, plugging in 0 for y and plugging in 0 for x, we get 0 is less than or equal to -3. That's a false statement. So that means we would shade on the other side of that line. We know it's solid because we have less than or equal to, and we know because we tested the point 0, 0, and that gave us a false statement, we shade the other side so that my solution region is that region in purple. Now that means that every point in that region is going to give me a true statement. For example, if we tried the point 3, -2, if I plug that point into my equation, into my inequality, I'm going to get a true statement because that point is included in my solution region. So I'm going to plug that in. -2 is less than or equal to 2/3 times 3 minus 3. Now 2/3 times 3, the 3's will reduce, and I'm just left with 2 minus 3. And we had a less than or equal to -2 over here. So I have -2 is less than or equal to 2 minus 3 is a -1. -2 is less than or equal to -1, so I know that's a true statement, so that's where I would shade. Okay. We also have another method called the y-axis method. So in this example, what you're really looking for is the y-intercept. So in our linear inequality here, the y-intercept is where x is 0. So I would substitute x equal to 0 in that inequality. Now what happens when I do that is 2/3 times 0 is just 0. So it's exactly like covering up that x term, like it's not there at all. So my y-intercept is negative 3. Now, of course, if you remember about linear equations, this is in the form m times x plus b. So my b would be negative 3. Now, I need to look at my inequality. It says y values are less than or equal to negative 3. Well, that means all my y values have to be smaller than negative 3, so I would shade below my y-intercept. So you can see here, shading below my y-intercept. Okay, so you can see based on these two methods how we can find that solution region. Okay, let's look at a couple of different examples here. So for this first one, I have y is less than or equal to a negative 1/2 x plus 4. So first I need to graph that line. So I use my y-intercept at 4 and my slope of negative 1/2 to graph that line. It is a solid line because I have less than or equal to. Now I have to figure out where to shade. Now we're using the test point method here. So I need to find a point. Now that point needs to not be on my boundary line. So here I could choose 0, 0. 0, 0, if it's not on the line, is the easiest point to always test. So I would plug in 0 for y, less than, now when I put in 0 for x, that term goes away, and I have 0 is less than or equal to 4. That is a true statement. Since that's a true statement, I know I'm going to shade below that line, because that is the region that contains that point. Now I'm going to look at my next equation. Y is greater than 3x. So I have this equation, or this line. My y-intercept is 0, and I have a slope of 3. Now I need to figure out where to shade. So I'm going to test a point. So notice here I can't choose 0, 0 because 0, 0 is contained on my boundary line. So I need to pick another point. So I'm going to pick the point 1, 1. So I'm going to plug in 1, 1. So 1 for y is greater than 3 times 1. 3 times 1 is 3, so 1 is greater than 3. Well, that's a false statement. 1 is not bigger than 3. So instead, what I'm needing to do is shade on the opposite side from where that test point is. So my test point is here, so I need to shade on the other side of that line. Okay. Now we're going to look at our y-axis method. So I'm going to graph the line for my boundary line, y equals x plus 3. So here's my equation. Notice it is a dashed line because I have strictly greater than. Now, in order to figure out where to shade, I need to figure out what my y-intercept is. So I'm just going to cross out my x term, and notice my y-intercept is 3. So I know I have to have y values that are larger than 3. Well, all values on my y-axis are larger than 3 above that line. So I'm going to choose to shade above that line, because that is the side of the line that contains those values that are bigger than 3 on my y-axis. Okay, next I have y is less than or equal to 5x. Okay, so I have a y-intercept of 0 here. If I cover up or cross out my x term, I'm left with 0. So my y-intercept is 0 here. So where is y less than or equal to 0? Well, all values on my y-axis are less than 0 here. So I know I'm going to shade on this side of my line. Okay, next we're going to talk about a system of inequalities. Now, in order to understand how to graph the system of inequalities, you really need to understand what the solution to an inequality looks like. So again, the solution to an inequality is not just a point or just a single value. It's the entire region that is graphed that we've shaded in. So it's this entire region. I'm kind of moving it around on purpose here so you can to really emphasize that every point in that region is a solution to that inequality. So any point in here is a solution. So when we graph a system of inequalities, what I'm really looking for is where these solutions work for both equations. Now, when we look at a system of equations, we're looking at just where they cross. So here I have this inequality graphed over here with its feasible region or its solution region shaded below. Then I have this equation where I've shaded above. And notice here, this is the solution to the system of inequalities. When we graph both of those regions for the solutions, this solution feasible region is where both of those inequalities are true. So essentially, it's where the solutions overlap. So it's where those solutions cross. So what we're going to do next is we're going to look at linear programming. And this really uses that system of inequalities a little bit more. So we're going to look at a method here for linear programming. But first I want to describe a little bit what linear programming is. So what is linear programming? It means we're going to maximize or minimize a function when given some constraints. So when we talk about 7.3, we're really going to talk about contextual applications of linear programming, but you need to understand the math behind it first. So we're trying to maximize or minimize. So we're trying to find the highest or lowest values for each of these what we call objective equations or objective functions. So our method here is first to identify the objective function. Then we're going to list the constraints. That's going to be a system of inequalities based on constraints on cost or materials or other things in that situation. Then next, what you need to do is graph the feasible region. So find the solution region for that system of inequalities. So once you've graphed that feasible region, what you're going to see is you're going to see some corners. You're going to see some places where some of those inequalities meet. Those corners are where we're going to find our maximum or our minimum value. So we have what's called this corner point theorem. This corner point theorem tells me if a feasible region is bounded, That means that it's closed. It's completely bounded by our constraints. Then we're going to have our corners, and we'll find those through various methods. Our corners are going to give us our maximum or minimum values. When we have a region that is completely bounded, that means completely closed. We're going to have both a maximum and a minimum. If we have our feasible region that is unbounded, that means it's not completely closed. We'll still have corners, but we may only have a maximum. We may only have a minimum. We'll only have one or the other. Now, if it exists, it will still occur at one of those corners. Okay, now to find out which one is the max or min, we're going to plug into our objective function those corner points. Okay, so we're going to look at this example. This is one where we've already found our feasible region. We've already graphed all of our inequalities, and in all of your examples it will give you your inequalities. When we do 7.3, we're going to be coming up with those inequalities ourselves, and you'll have a little bit of practice from 7.1 on those word problems on setting up inequalities from our word problems. Now, once we have our feasible region, now you can see here that it's in blue. That is our system of inequalities region. Now, we have a closed bounded region. So we're going to have both a max and a min. Now we figure those out by testing our points in our function. So here I'm going to test the points by plugging them into our objective equation. So this is my objective function or objective equation here. In your homework problems, it will tell you what your objective equation is. Okay, so here's my objective equation. I'm going to plug in these x and y values and find the z value for each of those. So if I plug in 0, 0, that means 0 for x and 0 for y, I get 0. If I plug in 0 and 15, that means 0 for x and 15 for y. So let's figure this out here. Let me open up my calculator. Sorry, my calculator's taking a while. Okay, here we go. Sorry guys, technical difficulties. Alright, here we go. So, what I'm going to do here is I'm going to plug in 0.4 times 0 plus 0.75 times 15. And I get 11.25. Okay, next I need to try 618. So 0.4 times 6 plus 0.75 times 18. And I get 15.9. Okay, now I need to try 10, 9. Okay, 0.4 times 10 plus 0.75 times 9. 10.75. Last one. 0.4 times 12 plus 0.75 times 0. We get 4.8. Now, from these z values, what you can see is where my minimum and maximum values are. So, from my values here, I notice that I have a lowest value at 0, 0. That means this is my minimum. Now I notice here at 618, I have my maximum. So once I found my corners, now I can see that my maximum occurs at 618, my minimum occurs at 0, 0. Now here in this example we see an unbounded region. So notice here that I have my corners and I'll only have a minimum value here. So what I'm going to do is I'm going to test each one of these and I'm going to see where my minimum is. I'm only going to do part A here. So I'm going to use my objective equation and I'm going to see where my minimum occurs. So I'm going to say z equals 4x plus y. So 4 times 0, I'm going to start with 0, 10. 4 times 0 is 0, plus 10 is 10. Okay. 2, 4. 2 times 4 is 8, plus 4 is 12. 5 and 2. 5 times 4 is 20. 20 plus 2 is 22. And then I have 15, 0. 15 times 4 is 60. 60 plus 0 is 60. Now you can see here, because this region is not bounded, this is going to keep going. Even though you can't see it, it's only because of how much of the graph I'm showing. I can see here that I'm going to have a minimum value at 0, 10. Now, one thing I want to kind of cover here is being able to solve a linear programming problem graphically, looking at the steps one by one. So write the objective function and all necessary constraints. You're going to graph the feasible region. Determine the coordinates of each of the corner points. Find the value of the objective function at each corner. Then numbers 5 and 6 depend on whether the region is bounded or unbounded. Okay, so number 5 says if the feasible region is bounded, the solution is given by the corner point producing the optimum value of the objective function. Okay, so whether you're finding the minimum or the maximum value. The minimum or maximum is going to occur at one of those corner points. Now, if the feasible region is unbounded, in the first quadrant and both coefficients of the objective function are positive, then the minimum value of the objective function occurs at a corner point and there is no maximum value. So just like in our previous example here, notice both coefficients were positive. We were looking for our minimum value here. Okay, we're going to have an example here. So we're maximizing this equation subject to these constraints. Okay, so these are my constraints. These are my inequalities that I need to graph here. Alright, so what I'm going to do is I'm going to graph these inequalities. Before I can do that, I need to adjust this inequality so that it's y equals so that I can graph that. So I need to solve for y. So I'm going to move my 2x term over and divide by 3. So I'm going to have y is less than or equal to negative 2x plus 100 over 3. Oh, excuse me. 2/3 x plus 100 over 3. Okay. Next I have y is less than or equal to negative 5/4 x, and 200 divided by 4 is 50. You can find these equations very simply by just solving each of those inequalities for y. Okay, now I have my x-axis and y-axis. I'm going to scale by 5s. So I have 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. Okay, and so on and so forth. So here I have 10, 20, 30, 40, and 50. Okay, so I'm going to graph my inequalities. So first I have 100/3. That's about 33 1/3. So I know my y-intercept for that is here. And I have a slope of negative 2/3. Now one way that you can look at this is you can actually find the intercepts of each of these and then connect the two intercepts. So notice here in my first equation I have 2x plus 3y equals 100. When x equals 0, that's my y-intercept. When y equals 0, that's my x-intercept. So all I have to do is cover up each one of those. So to find my x-intercept, just cover up your y term. So 100 divided by 2, x would equal 50. So my x-intercept here is 50. My y-intercept, cover up the x term, 100 divided by 3 is 33 1/3. So I can connect those 2 points, 33 1/3 and 50. Now, one thing about this line is it needs to be solid. Okay, next, I'm going to cover up my y term to get my x-intercept. 200 divided by 5 is 40. I believe. Okay. So I know my x-intercept is going to be 40. Cover up my x term. 200 divided by 4 is 50, so that's my y-intercept. So I'm going to graph connecting to 50 on my y-intercept to 40 on my x-intercept. Okay, so there's the first two. Y is greater than or equal to 10. Well, y equals 10 is just a horizontal line, so I'm going to graph just a horizontal at 10. X equals 20 is a vertical line through 20. So 5, 10, 15, 20. I'm going to draw a vertical line through that. Now I need to figure out where my feasible region is. So this is where I'm going to look at each one of these inequalities individually. Excuse me. Now this is where each one of those methods, the testing point and things like that would come in. So I'm going to see here that my graph on this first equation is going to need to be shaded below because it's less than. So I'm going to shade below that. Okay. For my next equation, for my pink, I'm also shading below. You can start to see where those pink and greens overlap. Then y is going to be greater than 10. I shade above. Made it too transparent. And x greater than 20, I shade to the right. So you can see that feasible region. Okay, so let me actually clean some of this mess up. You can see where all 4 of those overlap. Is actually in just that region. So this is the feasible region that I'm going to be looking at to find the corners and then find my maximum. So what I need to look at here is how to find those corners? Well, all of these corners are intersections of two of my inequalities. So here I'm going to find a corner at an intersection of each one of my x and y. Notice I counted by 5, so this is 5, 10, 15, 20, and this is 10. So I have a corner at 20, 10. Okay, I also have another corner here. I can see that that is 20 and 20. Now, to verify this, how would I know whether that is where exactly they cross? Now notice this is my pink. Maybe I should have color coded this a little bit. My pink was that very first equation. My green was this equation, and then this was my horizontal and my vertical. Okay, so notice here at 2020, that is the intersection of 20, my vertical, and my pink. To verify those, what I can actually do is I can see where that system of equations would be equal. So what I can do is I can actually say, well, what if I had the equation x equals 20 and the equation 2x plus 3y equals 100? And where would those two be equal? Okay, so that's what I would solve. Now, notice for my pink and green, what I'm going to have to do here is I'm going to have to solve that system of equations. So I'm going to find the solution to that system. Now I'm going to go back to what my y equals equations were on those. So I had y equals negative 2/3 over 3. And I also had y equals a negative 5/4 x plus 50. Now, to solve that system of equations, notice they're both equal to y, so I can set them equal to each other. So negative 2/3 x plus 100 over 3 equals negative 5/4 x plus 50. Now why my 4 doesn't want to write correctly? Okay. So what I'm going to do first is I'm actually going to multiply everything by 12. The reason is that I can get rid of all of my fractions. So what that's going to give me is a negative 8x plus 400 equals negative 15x that's not what I want to do. and 12 times 5 is 60, so 600. Okay, so now I'm going to solve the system of equations here. So I'm going to add 15 to both sides, so that's going to give me 7x. I'm going to subtract the 400 on the other side. And get 200. So 200 divided by 7, let's see what that is. No, 28.57. Okay, I'm going to leave it as 200 over 7. Now I need to find the y value. So I'm going to plug that back in to one of my equations. So I'm going to have negative 2/3 times 200 over 7 plus 100 over 3, and I get 100 over 7. So that's my next corner. And that last corner is the solution between my green and my horizontal. Okay, so that's where y is 10. So y equals 10. Then we have 5x plus 4y equals 200. So 5x plus 40 equals 200. Okay, so subtract 40, so 5x equals 160. 160 divided by 5 is 32. And y is 10, because we already found that. Okay, so my next corner is 32, 10. Alright, so now I have each one of my corners. Now, in order to maximize, I need to plug each one of those corners into my objective function. So I'm only going to do a couple here. Z equals x plus 3y. So I'm going to plug in 2010 to that. So z equals 20 plus 3 times 10. Well, 3 times 10 is 30. 20 plus 30 is 50. So this is the z value for my corner 2010. Okay, So let's try another one. Z equals 200 over 7 plus 3 times 100 over 7. Well, 200 over 7, 3 times 100 over 7 is 300 over 7. So that is 500 over 7. Okay. Which you can see is about 71. Okay, if we went through and did all of these, you should see that the maximum is 71. Okay? Here's your assignment. Make sure you use graph paper for your assignment. If you need graph paper, I have some. Just make sure to ask me.